Okay. Okay, hear me? Okay, great. Okay. Yeah, hello everyone. Thank you all for coming today. My name is Allison, and I'm super excited to be here to talk about faster PySpark with Apache Arrow. So just a quick introduction about me. I'm currently an engineer on the PySpark team at Databricks. And I'm also a Apache Spark committer, and I'm primarily focusing on Spark SQL and PySpark. So previously, I was on the data team at Robinhood, and also did database research at Carnegie Mellon University. So I'm very passionate about databases, distributed systems, and basically the open source community in general. And outside of work, I enjoy hiking, traveling, and taking city walks. So I'm very excited to visit New York City again. Yep. Okay, so here is what we're going to talk about today. So we're going to start with a quick introduction to Apache Arrow and PySpark. And then we're going to have a deep dive into one of the features in PySpark. It's called Python user-defined functions. And we're going to talk about how Apache Arrow can speed up the computations there. And then we will show more ways that Arrow is used in PySpark. And we will have some time at the end for Q&A. So by the end of the talk, you will have a better understanding of how Arrow can improve performance and how you can leverage Arrow-enabled features in PySpark. Okay. So let's begin with a brief overview of Apache Arrow and PySpark. So what is Apache Arrow? So here are some common definitions that you can find online. So Apache Arrow is a language-agnostic framework to process and transport large datasets. And it is designed to improve efficiency of moving data between systems and programming languages. And it is known for the in-memory columnar format, which allows for faster and standardized representation of structured data. So when I first saw this definition, it felt a bit abstract. Right? What exactly is Arrow, and how does it work? And how can we actually use it? So I won't go into too much technical details about Apache Arrow in this talk, but I do want to explore it from a more practical perspective by giving you examples in PySpark and show you how it works in real scenarios. Okay, so here's a quick intro to Spark. Spark is an open source, unified data processing engine, and it was started as a UC Berkeley research project and has been with the Apache Software Foundation for over 11 years now. It is production grade and is widely adopted by many of the companies, including 80% of the Fortune 500. And it supports many different programming languages, such as SQL, Python, Scala, and R. So you can use it both on your local laptop and also scale up to a distributed clusters with thousands of nodes to handle petabytes of data. And the open source Spark community is very active. So there are with more than 3,700 contributors from both the industry and academia all over the world. Okay, so the PySpark is the Python API for Apache Spark. It supports all the major Spark features, such as Spark SQL, data frame APIs, structured streaming, and machine learning. And it also has this Pandas on Spark API, which allows you to scale the Pandas workload by running it distributedly across multiple nodes. So PySpark is very popular. It has more than 30 million downloads on PyPy monthly. And it's actually super easy to get started. You just pip install PySpark, and it will just work. And you can also install this additional SQL dependency, which will install the pandas and PyArrow dependency for you. It is very important if you want to use all the Arrow optimized features in PySpark. So after you install PySpark, you can use the interactive shell to either use the data frame API or use the SQL API to do any data transformations. Okay, so now let's talk about PySpark user-defined functions. So Python user-defined functions, or UDFs, are one of the most popular features in PySpark because they're super easy to use. It's very similar to defining a regular Python function here, and all you need to do is to decorate this Python function with this UDF decorator and give it a return type. And then you can use it by incorporating into any of your Spark pipelines or logic. For instance, you can, so here's an example definition of the Python UDF. You can either use it in the data frame API, or you can register it in the current Spark session and use it together with the SQL queries. So another thing that's very powerful about Python UDF is that you can use any arbitrary Python libraries, right? So it gives you this very powerful Python ecosystems when you're doing all these data transformations. However, despite their usefulness, Python UDFs are pretty controversial. So if you search online, there are many blog posts and discussions advising against using Python UDFs. Why? Because they are often considered as very slow and have bad performance. And there are pretty much two main reasons for this. So the first one is that it has this performance overhead. So to use a Python UDF, you have to create separate Python processes, and then which will cost this, will have this actual cost of transferring the data between the JVM process and the Python process. And then it's the row-wise execution. So basically, Python UDF executes it row by row, so which can be pretty slow for large data sets. Okay, so we're going to take a closer look at how Python UDF works in Spark. So Spark pretty much executes this data frame across many executors, which run on the Java virtual machine, or JVM. And each executor handles a portion of the data in parallel. So when you use a Python UDF in your pipeline, Spark needs to first create a Python walker, which are just the separate processes running on the same executor node, and then send the data from these JVM-based executor processes to the Python walkers. So before rows are sent to the Python walker, Spark needs to convert them into a format that Python walker can understand. And this process is called serialization, which essentially converts a Spark internal row into a format that Python can use. So here, Spark uses this the pickle format, which is a pretty standard protocol for serialization in Python. So this process is often called pickling. So the pickled rows are then transferred from the JVM process to the Python worker side over a socket connection. And on the Python worker side, the rows are deserialized, processed by the UDF, and then results are serialized back again and sent it back to the Spark executor. So this back and forth, serialization and deserialization, or SERDE, creates a lot of overhead. So the pickle module here that we use in Python is more of a general purpose serializer. And it can handle any arbitrary Python objects, such as classes and functions, but it's not really optimized for performance. So when you have millions or billions of rows, this overhead can quickly add up and slowing down the entire Python UDF execution. Okay, so based on the definition of Apache Arrow that we just saw earlier, it seems that we can just use Arrow to reduce the overhead here. And that's exactly correct. So now, introducing a new type of UDF in Spark. It's called Arrow Optimized Python UDFs. So this is actually a new feature introduced in Spark 3.5, and it's actually very similar to the pickled Python UDF. You just need to set this use arrow parameter to true to turn a regular Python UDF into an arrow optimized UDF. Or you can, if you want to enable this arrow optimizations for all the UDF in your Spark pipeline, you can just set this configuration globally. And here is how Arrow optimized UDF works. So instead of using this pickle module to serialize the data between Spark executors and the Python walker, we use the Arrow record batches, which allows more efficient data transfers between these processes. So here is how it works. Spark first converts a batch of internal rows into Arrow record batches, and then stream them to the Python walker side. And the Python walker uses them for the UDF executions, and then once it's completed, they send them back to the JVM using the same Arrow format. So Arrow here is much faster than Pickle because it's more of a specialized format. It uses this in-memory columnar format, right, which is optimized for structured data, has better compressions. So this reduces the serialization cost between the transfer between the JVM and the Python walker, and overall speed up the data transfers and improve the UDF executions. And here is a benchmark showing the difference here, the performance difference here. So we're using the same function, the +1 function here, and the test was running on a single node machine with 4 cores and 30 gigabytes of memory. So you can see from the graph, Arrow Python UDFs are 1.6 times faster compared to the regular Python UDFs by just enabling this one parameter to turn your regular Python UDF to an Arrow optimized Python UDF. Okay, so here, note that Arrow Python UDF still executes row by row on the Python walker side. So can we do even better here? The answer is yes, and it's with this pandas UDFs. So this is actually not a new feature. It was actually presented at the same conference back in 2017. So it's 7 years ago. So while pandas UDFs can be a little bit more complicated than Python UDFs, they often offer even greater speedups by leveraging this vectorized operations. So you can see how to define a pandas UDF here. You just import this pandas UDF function, and you can, it's very similar to Python UDFs, but the only difference here is instead of taking this Python object, it actually takes in a pandas series or data frames as the input and output. So there are actually many different types of pandas UDFs. So this is just one of them. So the type hints here are actually required to help Spark infer what type of pandas UDFs being processed. And in the function body, you can just use the pandas vectorized operations to speed up the computation. So for example, here is the same +1 function that we discussed earlier, but we're operating on this column level instead of row by row. So you can see this v.add1 is a vectorized operation. And here's how pandas UDF works. So they're also using Arrow to transfer the data between the JVM and the Python process. But unlike the regular Python UDFs, pandas UDFs allow you to apply vectorized computation directly using the pandas API. And let's have a performance comparison. So here's a performance benchmark that shows the performance difference between the pickled Python UDF, Arrow optimized UDFs, and pandas UDFs, all using the same function, +1. And you can see here that pandas UDFs are 3 times faster than the regular Python UDFs. And it's around 1.8 times faster than the Arrow optimized UDFs. So this clearly shows the power of vectorization. But the +1 function that we saw earlier was just a very simple example. So now let's take a look at a more complex case here. Suppose we're calculating the cumulative distribution function, or CDF, Here we're directly using the SciPy library. And this graph shows a huge performance difference. So Pandas UDFs is about 150 times faster than Python UDFs. 150 times faster than Pandas, than Python UDFs. Okay. Okay, yeah. So this is because the SciPy library can take full advantage of vectorization, making the calculation much faster. So for certain computations, Pandas UDFs can be significantly more performant than Python UDFs. Okay, so here is another type of Pandas UDF that I want to cover, the Pandas iterator UDFs. So you might be thinking that this is really complicated, like why do I need this? But this can be extremely useful if under certain circumstances. So unlike the Pandas UDFs we discussed earlier, which process one series at a time, so this Pandas iterator UDFs can take an iterator of Pandas series or data frames as input and output. So the cool thing about Pandas iterator UDFs is that it allows you to do this very costly initialization at the very beginning before processing your input rows. And then you can reuse the initialized state across multiple execution across multiple batches. So this is particularly useful if you want to deal with like network operations, for instance, talking to an external service or establishing a connection to a database. So instead of recreating this connection every single time you process a batch, this Pandas iterator UDF allows it to be created only once, and then reuse this connection over multiple executions, and then clean up the connection at the very end. So it will help you to manage the connections and resources properly. So using this Pandas iterator UDFs can further speed up the UDF computation depending on your need. Okay, so here are some key takeaways. So first, always use PySpark's built-in UDFs or SQL UDFs. They are much, much faster because they just run directly in JVM. Like you don't even need a separate Python process here. So that just eliminates the entire overhead of having the Python processes. But sometimes Python UDFs can be very useful, and you might actually want to use it in your pipeline. So be very cautious when you're using these pickled Python UDFs, because they could be slow, and there could be lots of serialization overheads, and they execute row by row. So if you're using any version for Spark, like about Spark 3.5, choose to use the Arrow optimized Python UDFs for better performance, because Arrow just simply reduces the data transfer cost between the JVM and the Python process. And if your computation can leverage the vectorized operations, use Pandas UDFs, because they can give you even more speedups. Yeah, and finally, use Arrow for faster serializations and data transfer between processes. Okay, so UDFs are not the only feature in Spark where it leverages Apache Arrow, right? So now let's explore more features that Arrow is used in PySpark. Okay, so the first feature I want to cover is mapping Arrow. So this is a newly introduced feature in Spark 3.3. It's a new data frame API where it allows you to apply custom transformations directly on top of a Spark data frame using Arrow. So for instance, you can see that this function takes in an iterator of Arrow record batch and applies it to every single partition of the data frame and returns another iterator of Arrow record batch. So this is very useful if you, for more advanced users, if you need more control over batch processing, and if you want to leverage Arrow's rich ecosystem for data transformations and machine learning use cases. Okay, so the next one I want to cover is the data frame to Arrow function. And it's going to be in the upcoming Spark 4.0 release. So previously, Spark only has this to pandas function, which converts a Spark data frame into a pandas data frame. But now we have this direct API to convert a Spark data frame to an Arrow table. So this allows you to even seamlessly integrate with the rest of the Arrow ecosystems on top of Spark. Okay, so the last feature that I want to cover today is the new data source API, which is also going to be in the upcoming Spark 4.0 release. So this API allows you to build custom Spark connectors to read from and write to external data systems. So previously, Spark only has this JVM or Scala API for data sources, which can have a very steep learning curve. But now, with this Python data source API, it's much easier to build data sources and sinks for Spark just in Python. And this API supports both read and write operations with more advanced features like distributed scan, atomic writes, and they also leverage Apache Arrow for efficient serialization and deserializations. And it supports both batch and streaming, and making it very flexible for various use cases. And you can just directly use it with Spark's read and write API here. So one key benefit here is that you can build this data source once, and you can use it across multiple different programming languages, and it can be pip installed, it can be packaged and pip installed, allowing it to be shared with others very easily. Okay, so I'm going to give a very concrete example here. So this is an example of a custom data source that reads a Hugging Face dataset. So Hugging Face dataset is a library for accessing and sharing data for machine learning use cases. And here you can very easily just pip install this example package called PySpark data sources with this dataset dependency. So by the way, you can scan this QR code here to see the source code of this implementation. So after you install this package, you can import the Hugging Face datasets and register it in the current Spark session. So once it's registered, you can use Spark's data frame read API to read from this data source. So for instance, here we're reading from the Hugging Face data source, and load any arbitrary Hugging Face datasets as a Spark data frame. So for instance, we're loading the Rotten Tomatoes dataset, and you can see that the data frame right here. So this is just an example highlighting how easy it is to use a custom data source and how easily these data sources can be shared to others. So again, you can scan this QR code to see more example implementation of the new Spark data sources. And here is a recent improvement to the Python data source API. It basically adds the support in the read function to directly return an iterator of Arrow record badges. So this can lead to even more speed up, especially if your underlying data sources is already using the Arrow format, as it eliminates the row to Arrow columnar batch conversion. And here's an example implementation of a data source that basically leveraged this new functionality, this new feature that returning an iterator of Arrow record batch. It basically reads data from DuckDB using the ADBC API, so which is a standard database API that helps data systems talk to each other using Arrow. So as you can see here, this is like the full source code of this data source. This fully functional data source is literally written in less than 20 lines of code. So in this example, we define a .db data source with a name and a return schema. And then in the data source reader, we establish a connection to a .db through the ADBC driver, execute the query, and then fetch the results directly as an iterator of Arrow record batch. And you can easily use this data source in Spark to load the data. So this is just a start. We can build many connectors for Spark using this new data source API, and we can leverage Arrow's rich ecosystem and easily package them and share these connectors with others on PyPy. Okay, so to wrap it up, Apache Arrow is incredibly useful for reducing the serialization and data transfer costs between different systems and programming languages. And there are many Arrow-optimized features in PySpark that we can use to speed up the computations. So for instance, the Arrow Python UDFs, Pandas UDFs, and Python Data Source API. So definitely try them out. And last but not least, Spark has a very active community. Many of the features that I mentioned earlier are actually from our community members from various organizations. So we welcome more ideas and contributions to help both projects grow and evolve. Okay, that's all. Thank you. Yeah, any questions? Or you can talk offline.
Would there be any benefit to using Arrow or Spark file to use regular Spark function?
Use Arrow data source.
But so when I'm setting my data into Spark, if I get it in an Arrow format and start processing it, just using regular Spark functions, would there be a benefit over using Arrow versus Parquet?
So there's so currently Spark only has this 2 Arrow function, right? It doesn't support Arrow directly as a data source. So Parquet is still more performant because it's literally a columnar format. Yeah. So we could add Arrow data source. Yeah.
How does Spark using Apache Arrow compared to Apache Data Fusion?
Oh, that's a great question. So, okay, it's so do you remember this graph where you have the JVM layer, right?
Yeah, in
so
Python.
In Spark, you still have to convert the Spark's raw format into the Apache Arrow's record batch. So that conversion is also like, there's overhead during that conversion, right? So Data Fusion actually, you don't need to convert it because the internal format is already in this Arrow record batch. So it's basically, they don't have this, Spark is still using the internal rows, and Data Fusion is already using this Arrow record batch. So that's the difference.
So one step beyond this.
Exactly.
Thank you.
Does this mean if you write Spark code in Scala or Java that you would just avoid this problem entirely?
Yes. You can use a Python UDF in your if you're using Java or Scala. So if you want to leverage Python, which is very popular, yeah.